This video is going to continue on considering geometric properties of sections of materials that are important when we're looking specifically at beams, typically when we want to look at the stress distribution, either normal stresses, shear stresses, etc. So in the last video we covered centroids. As a reminder about that, the centroid of an object, whether it's the center of area if we're looking at 2 dimensions, or center of mass if we're looking at a 3-dimensional volume, that's the point about which all of whatever quantity you're looking at, whether it's mass or area, all of it is balanced. So if we think back to a rectangle, like 2-dimensionally shown here on paper, it's really easy to see the centroid of that. It's fairly intuitive to us, right? We find the axes of symmetry, and where they intersect, that's going to be our centroid. We, in the last video, looked at, okay, what if we want to go beyond that into more complicated shapes? And we talked about how we can use composite areas to find the centroid. So we looked at some areas, starting out with a basic rectangle, then we added a triangle on top of that rectangle, and look at how does that shift the centroid. Hopefully you remember it. Basically, it's if we had our original rectangle like this, and we add, and that centroid was here in the middle, when we add on some material to the top, we're going to have to shift the centroid towards that additional material to keep everything in balance. We also looked at other shapes where we subtracted some pieces to make a composite shape and found a centroid. So here again, if we look at the original rectangle, centroid's right at the center of the axis of symmetry. But then if we took out this rectangle up here on the top, then we're going to have to shift the centroid down a little bit, because now we're going to need to offset the weight that we've taken away here by moving a little bit this direction. So some of what used to be on this side of the centroid is now on that side, so it's all equal. And then lastly, we did a similar thing by taking a corner out. And once we did that, just as a reminder, now we have no symmetry. We don't have symmetry about x or y, so then we have to find the distance to the centroid in both x and y. So just a reminder, that's what centroids are about. And centroid is an easy to visualize thing, because you can empirically find the centroid of an object by just figuring out where it balances, right? So for an original standard rectangle, it's going to be right in the center of it. For our rectangle where we've cut out some on the top, if this was the original centroid, we figured out mathematically it shifted down along that axis of symmetry this much. And so then this one balances nicely right at that centroid. And then same thing on this third shape, the more complicated one, where now we don't have any axis of symmetry in x or y. So our original centroid that was here shifts a little bit this direction as far as y, and a little bit that direction as far as x, and then it should balance again, and it does. Okay, so that's a review of centroids. Now we're looking at moment of inertia. Moment of inertia is sometimes a bit of a hurdle when students first start working with it, because it's not really a physical property that you can go out and measure. It's not the balance point of an area. It's not the center of gravity of a volume. Basically, I think the most useful way to think about the moment of inertia of an object is its resistance to bending about a specific axis. And that's important to note, that about a specific axis part, because always when we're finding moment of inertia, it's about some axis, and we might need to know it about some different axis, and that's where we come in and use the parallel axis theorem to find that. So let's talk about the moment of inertia of some common shapes. Just like when we're doing the centroid, it's easy to see the centroid of a standard rectangle or circle or a triangle. It gets more complicated when we do shapes that are built up of multiple pieces, but we can usually, in engineering, break them down into a composite shape of multiple standard shapes. So here in the inside cover of your book, you'll typically have a chart that shows centroids, so showing you the distance of a centroid. So for circles and rectangles, it's just right in the dead center. There's no equation for that. For a semicircle, the distance to the centroid is 4/3 of the radius, all of that divided by pi. And then right next to it, in this column, we have the equation for the moment of inertia for these common shapes. So the most common one we'll work with is rectangles, and so the moment of inertia about the x-axis, so that's about, if we look at the shape relative to this axis here, is 1/12 base, so the width, times the height cubed. And that cubed factor is an important concept in beams, that you can see there's a much greater impact on the stiffness of a beam the further away from the axis you're bending you get. So let's say you doubled the base height, that's just going to double the total I, right? Whereas if you double the h, the distance away from the axis you're looking at, that's going to be 2 to the third, or 2 times 2, 4, 8 times 2, I'm sorry, 2 times 2, 4 times 2, 8. So you get an 8-fold increase for your moment of inertia if you increase height versus just a linear increase if you increase width. And that's why when you look at many engineering sections, they're basically maximized to put as much of the material as far away from the axis you're bending about as possible. Okay, let's get back to what we're talking about. So common equations for bending moment of inertia is Ix for a rectangle, 1/12 bh cubed. For a circle, 1/4 pi r to the 4th. Okay, so if we want to find composite, or let's start with a really simple one. If we're looking at that original rectangle that we worked with before here, we're looking at 1, so, and let's say we're bending about this axis. That's a key thing to talk about. When we say Ix, it's always about the centroidal axis. So again, looking back at this table, the moment of inertia for this rectangle is 1/12 bh cubed, and that's about bending about the centroidal axis. And so we just covered how to find centroids. We're not going to do that again. But another key idea is the neutral axis of a beam is always located at the centroid. So that's why we focus on centroids first, is we need to know where that centroid is, and that's where the moment of inertia is about, the default equation. So when we say Ix equals 1/12 bh cubed, this I is about this neutral axis. And so let's just plug in numbers for that for this one. In this case, that's 1/12. B, our B, that's the width parallel to the axis we care about, is 8 centimeters. And then the height is 10 centimeters. And that's cubed. Okay, so then let's plug that into a calculator. 8 times 10 cubed, all that divided by 12. So that answer is 666.66 repeating. And my units are centimeters times centimeters cubed. So the units are centimeters to the 4th. And so obviously that's not a physical dimension, right? There's no such thing as centimeters to the 4th that makes sense. And that comes back to me when I was talking about this isn't really a property that you can directly measure. It's useful. It functions in the equations the way we need it to, but you can't have a centimeter to the 4th power, right? We can go centimeters, that's a unit of length, centimeters squared, that's a unit of area, centimeters to the 3rd, centimeters cubed, that's an area of volume, centimeters to the 4th, that's useful, and we do need to use that because our units will cancel out correctly when we're doing the moment equation or shear equation, etc. Okay, so that is I for this particular shape about this centroidal axis. Key idea also is to keep in mind, it may be, I did it in centimeters here because that's the units I used when I was drawing it out, but in reality, if I were doing this for an engineering problem that I was actually going to solve, it might make better sense to do it in terms of meters so that when we plug in newtons for our force, etc., all our units work out correctly. So in that case, I would write it out as 1/12 base 8 centimeters is equal to 0.08 meters times 10 centimeters, that's 0.1 meters cubed. And so that should end up with the same number, 666, etc., but it's going to be different power, definitely. So 0.08 times 0.1 cubed divided by 12, and that comes out to 6.66 repeating times 10 to the negative 6 meters to the fourth. So it's the same representation of I, it's just whether my units are in centimeters to the fourth or meters to the fourth. Okay, so that's finding the moment of inertia about a centroidal axis. When we start looking at composite shapes, I may need to know it about a different axis. And before we even get into composite shapes, let's look at it about a different axis for this one single shape. So that's when we use the parallel axis theorem. And that says that I'm sorry, that's pretty sloppy. I about any axis, so let's say we want to do it about this axis down here that I'm going to call x prime. I about x prime is equal to I about the centroidal axis, so Ix, plus the area of the shape we're looking at times the distance from the centroidal axis, the centroid of the area to the new axis that I'm looking at, so about x prime. So in this case, this would be that distance. And it's that distance squared. So let's do that for this shape we have here. So I about x prime is equal to Ix, that's 1/12 base, and we'll just do it in centimeters for now. So base is still 8 times height cubed, so times 10 cubed, plus the area of it, so the area here is 8 times 10, so it's 80, times the distance from the centroid of the shape that I'm caring about to the axis that I'm trying to find I about. So in this case, that's the distance from the centroid to this axis, that's 5 centimeters times 5 equals. So we do that, 8 times 10 cubed divided by 12. I should get the same thing I got before, that's 666.66, and then plus 80 times 5. And so that is 1066.66 repeating centimeters to the fourth. So that's the parallel axis theorem. And there may be applications where you do it on a simple shape, but we're going to use it pretty much every time when we start looking at composite shapes. So let's do that next. And I guess actually before we go on and look at composite shapes, let's point out that this shape has different stiffnesses depending on whether we're bending about an axis parallel to x or an axis parallel to y. And so let's just plug in the numbers to that. If instead of finding out I about this axis, we want to find out I about this axis, we can use the same equation. It's going to be I is equal to 1/12 bh cubed. It's just now b and h are swapped. So it's 1/12. And now our base, because remember the base is always the length parallel to the axis that you're bending about. So it's 1/12 times 10 times 8 cubed. And so you can already see that it's going to be less stiff in bending about this axis than it was about this axis, right? Because we're same two numbers, 8 and 10. Just before we were cubing 10, and now we're cubing 8. So 8 cubed times 10 divided by 12. And the answer is 426.66 repeating centimeters to the fourth. So just pointing out again that a beam is always stiffer the more of its material is located further away from the axis you're bending about. Just to kind of demonstrate that, let's look at a beam. Let's say we took away 2 centimeters of width from this one and increased it in height so that now our beam was, I'm just going to draw it small this time. So we were 8 and 10. Now we're going to be 6 and 12. Let's look at the I for that. So total area, total material used for this one is 80. So area of the original, original equals 8 times 10 equals 80 centimeters squared. In the A for the new, I said it's take away 2 on that way, add 2. So we're looking at 6 times 12. That's 72 centimeters squared. So we're using less total material. And let's look at what happens to I, where its stiffness about bending. So I is going to be equal to 1/12 times the base. Our new base is 6 times 12 cubed. So 12 cubed times 6 divided by 12. And the answer is 864 centimeters to the fourth. So our original was 666 centimeters to the fourth, and that used 80 centimeters of material. By readjusting our dimensions of our beam, we went to 72 centimeters squared of material, and we got a stiffer beam. So that's why, again, just kind of talking about this, kind of trying to think ahead to why engineering shapes are the way they are. In original wood construction, you would see lots of beams, right? Just nice straight rectangular beams because they're easy to manufacture. And when you do that, you see beams installed vertically, right? With the longer dimension in the vertical direction as opposed to in the horizontal direction, because it's much stronger in this axis, in this direction of bending, where you're bending about a short versus where you're bending about the long dimension there. So then as we got into materials in engineering where we were actually able to tailor the shape of it, so if you think of that as steel beams, or even in wood construction, when they started getting into wood I-joists or web joists, the shape of the beam is typically something like that, where we're trying to use the material most efficiently so we get as much of the material as far away from the axis that we're bending about as possible. Because material that's down here close to the axis doesn't do us any good. So by cutting out some of this stuff in here and moving it up here, we can make the beam stronger for the same amount of material. And that's what a lot of engineering is finding the most efficient way to do something. So let's look now at some composite shapes like this I-beam here. So it was pretty easy to find centroid and I about a uniform shape, because on a uniform shape the I is about its own centroidal axis. Let's go ahead and look at an I-beam now, or an I shape. So for our first example of a composite I, or composite moment of inertia, we're going to use an I shape. So just don't get that. I'll try to be clear when I'm using I for the shape, an I-beam shape here, versus I representing our moment of inertia. So there's two different ways we can look at this I shape, starting either from the whole rectangle block that we've done before, right? We found I about a simple rectangular shape. We can now, we want to look at this composite I of just the I-beam shape. We can do that either by finding the whole rectangle one and then subtracting out these two sides, or we can build it out of three parts. And it's a little easier to start with to look at it as the whole rectangle and then take away the contribution of these two pieces along the side. So to get a sense of what I'm talking about there, let's look at first where the centroid of the whole rectangle is. So if you're looking at this 8 by 10 rectangle, we know that it's symmetric about its axis here, right? If we mirror it about this, it's symmetric. So that's one axis of symmetry. If I come across 4 at top and bottom and draw a line right down through that, that's one axis of symmetry. And then same thing if I come up each edge, 5. That's the other axis of symmetry. And so in this case, the centroid is at the intersection of those two, right there. So if we're thinking about it in terms of this being x and this being y-axis, along the x-axis, the coordinate would be 4 over, because we're 8. So centroid at 4, 5 for the whole rectangle. Okay, then let's look at some other pieces. We said we're going to look at the whole rectangle is one piece that we care about, so we found the centroid of that. And then we're going to, what we talked about is we're going to subtract some areas. So the first area we're going to cut away from this rectangle would be this section on the left side. And its centroid would be along that same axis, right? We have symmetry about that axis here, but now the centroid's no longer over in the middle, right? We're looking at the centroid of just this orange rectangle, so its center would be 1.5 over, since this distance is 3. So the centroid of that one is going to be right there. Okay, then the other area that we're going to subtract would be this part over here, and same thing for it. Its centroid is easy to find. So there are the centroids of the whole rectangle. The left part we're going to subtract, and the right part we're going to subtract. And why I'm marking those out right now is, as we get started, when we're looking at I, or the moment of inertia, we can add and subtract the composite moment of inertia of each piece to come up with a total. Or, so in this case, we're going to take the moment of inertia of the whole rectangle and then subtract each of these sides here. And since after we subtract those out, the centroid of this I shape, basically if these pieces are gone, hopefully you can see they're still symmetrical about this two axes. So the centroid of the final shape is no different than the centroid of the original rectangle. And that makes it simpler than what we're going to do later on if we look at a different shape. Let's say if we look at a T-beam, it's no longer the final shape. If we said we're going to make a T-beam that comes through, the final shape centroid no longer would be right where the original one. And that's when we have to move into the parallel axis theorem. So doing it this way, whole rectangle, and then subtracting out two pieces that are still symmetric is kind of an easy step into finding composite eyes. So let's get started about that. So first we're going to find I for the whole rectangle. And hopefully you can remember what that is related to. I for the whole rectangle, so I'll just call that I blue here, is equal to 1/12 the base, the distance parallel to the axis we're bending about. So that is 1/12 times the base of 8 centimeters times the height cubed, so times 10 cubed. And that's going to be equal to, we solved it before, but we'll just do it again, 10 cubed times 8 divided by 12. So if we're working in units of centimeters, that's going to be 666.66 repeating centimeters to the 4th power. And again, centimeters to the 4th doesn't make sense intuitively as a physical property, right? And we talked about that. The moment of inertia is not a physical property that makes sense as far as units. It's not a mass, it's not a volume. You know, if you think about centimeters, a centimeter to this 1st power is a length, centimeters squared is an area, centimeters cubed is a volume. Centimeters to the 4th is not a realistic physical representation, but the units are consistent so that when we plug them into, say, the moment equation or the shear equation, we do need to keep in mind that the units of I are a length unit to the 4th power, whether that's meters to the 4th, inches to the 4th, feet to the 4th, etc. Okay, so we found I for the big rectangle about the big rectangle's neutral axis, which happens to be the neutral axis of our composite shape as well, so we don't have to use the parallel axis theorem. I'm going to keep kind of harping on that on this one because this is one of the few instances where we don't need to. Let's just reiterate that. You don't need to use the parallel axis theorem if the centroid of the component piece that you're looking at is along the line of the centroid of the final shape as well. So let's look at that for the I about this axis, which runs through its centroid. So again, we won't need to use the parallel axis theorem. So I orange is equal to 1/12 the base distance parallel to the axis we're looking about, so that's 3 centimeters, times the height, that's 8 centimeters cubed. So 8 to the third times 3 divided by 12, it's equal to 128 centimeters to the fourth. Hopefully you can see that the purple is going to be just the same. I purple is 1/12 times its base is 3 times its height is 8. So it's also going to be 128 centimeters to the fourth. Okay, so let's talk about that a little more. I did it twice. Really, it would have been just fine to say find out the component I of the orange part and then just multiply it times 2. It'd be the same thing. I just want to stop here for a minute and talk about, let's say rather than finding I about this axis parallel to the x, we were looking at bending along this axis of symmetry. In that case, you'll note that the centroidal point of the purple and the orange is not along the axis that we're looking at, the bending axis of the final shape. So in that case, I would have to use the parallel axis theorem. And so we'll look at that in the future, but just pointing out, the reason I'm able to avoid using parallel axis theorem when I'm looking at it bending about this axis is that the centroid of each of the pieces I'm looking at runs through the neutral axis of the whole composite shape. Okay, so we've got all the information we now need to find I total for the composite shape. We'll do that in different color blue here. So I total is equal to the large I that we found, so 666.66 repeating, minus 128 minus, minus 128 equals, so 666.66 minus 128 times 2. That comes out to 410.66 centimeters to the fourth. Okay, so that is I about our neutral axis bending in the direction of x. While we're here, actually we'll just leave that for now. I was going to say we could find I about if we were bending about an axis parallel to y, but we'll save that. Let's kind of go into this in more bite-sized chunks. So if we're done looking at finding that I from taking the whole I of the whole rectangle and subtracting the I of these component pieces, I told you there's another way we could have done it, and that's by building I out of the individual pieces instead of taking a large piece and subtracting them out. So to do that, let's break this into different shapes. So let's separate the top flange into one shape, bottom flange into one shape, and then start finding the components. So we'll look at this one. It's an area in yellow. We'll have okay, so now we've got 3 areas. So let's go ahead and find the contribution that each of these 3 areas make. And we know that the neutral axis or the centroid of this shape, the final shape, hasn't changed, right? It's still symmetric about a line right down the middle. And then we know the centroid's going to be also mirrored this way across here. So we can find that point. If it's overall 10, it's going to be up 5 centimeters still. So centroid is right there. So that's our neutral axis, because I is always about the centroid or neutral axis of the final shape. That'll become more clear why I'm highlighting that when we go to another shape where the centroid is not in the same location as the original parent shape. Okay, so now let's start looking at the individual components of I. So we start out with the I of this yellow shape at the top. So I yellow is equal to 1/12 its base, so that's the width parallel to the axis we're bending about, so that's going to be 8, times its height cubed, that's 1 cubed. But now, so that I is about a centroid right through there, right? That I that we just wrote, that part right there, is about that axis. Before, when we were doing it up here, all the shapes we were looking at, the big rectangle, the centroid was right through there. The orange, the centroid was through the neutral axis. Now we have a component that's about its own neutral axis, which is different than the axis we care about. So now I do need to use the parallel axis theorem, because I want to know what contribution does this 1/12 times 8 times 1 cubed have about this axis, an axis parallel to its own centroidal axis, but some distance away. So remember the terms for the parallel axis theorem. Let me write that right up above it. I about some axis is equal to the component I about its own neutral axis plus the area that we're working with times the distance squared. And the distance is the distance from the centroid of the area that we're looking at to the axis that I care about, to this axis. So in this case, that's going to be plus the area of this top flange, which is 8 times 1, so that's 8 centimeters squared, times the distance from this centroid to this one. So distance from there, from here to here, is 5, and then we come back down 1/2 to get to the centroid of the yellow flange. So that's going to be times 4.5 squared equals. Okay, so let's figure out what that is. 1 cubed is going to be 1 times 8 divided by 12. So this part right here comes out to 2/3, then plus 8 times 4.5 squared. So all that comes out to, it looks like 162.66 repeating centimeters to the fourth. That's the contribution of this yellow one. I'm just going to right now write out right underneath it the contribution for the similar shaped, similar symmetric flange at the bottom. I equals 1/12 times 8, right? The base is 8, times the height cubed, that's 1, plus the area, times the distance from this centroid up to the neutral axis of the whole entire thing. So again, that's 4.5 squared. It's all going to equal the same thing, 162.66 repeating centimeters to the fourth. Okay, so just highlighting, this is the first time we've had to use the parallel axis theorem, because the component piece that we looked at, its centroid was located some distance away from the axis that I care about, which is the neutral axis of the final shape. Okay, last part now is I of the center web. I is equal to 1/12 times its base is 8 minus 6, so 2, times its height is 8 cubed. And now its centroid is located right there, which is along the neutral axis of the full shape. So that's the one I care about. So there's no plus AD squared for this, right? This component piece shares its centroid along the neutral axis of the entire shape. So no plus AD squared for this part. 8 cubed times 2 divided by 12. So that equals 85.33 centimeters to the fourth. Okay, add all that up. I total is equal to 85.33 centimeters to the fourth plus 162.66 centimeters to the fourth plus another 162.66 centimeters to the fourth. And that comes out to I total equals 85.33 plus 2 times 162.66. That equals 410.66 centimeters to the fourth. Okay, you can see we get the same value, 410.66, whether we do it by finding I of the whole rectangle and subtracting out 2 pieces, or if we do it by building it out of 1 center web and 2 flanges top and bottom. The final I, no matter how you do it, should come out to the same value because it's the same shape that we're finding I for. So that's our first kind of composite I using a I-shaped beam. Okay, let's go on and look at our next slightly more complicated shape. So we've done an I shape. Now let's look at a T shape. So let's look at this I shape. And again, it's as we're looking at it as this T shape, looking at it from within our same 8 by 10 outer rectangle. But now we're saying we're going to cut out these 2 sides and not leave a flange on the bottom. So we'll just end up with a T shape. Let's think about what that means before we start doing much math. Let's mark out on here the location of the centroid of the overall rectangle. Again, just like always, that's going to be at 4, 5. So 4 in the x direction, 5 in the y. So here's our one axis of symmetry. And there is, so this dot is the centroid of the whole rectangle. What's different about this as opposed to the I shape is the final composite shape, the T, the centroid is not located along that same neutral axis. So if this is the neutral axis for the big rectangle, right, because it's symmetric, if you ignore the T shape, that the rectangle is symmetric about both this direction and this direction. The T shape is not symmetric. The big rectangle is, but the T shape isn't, right? If you mirrored the T around this line, we're missing these pieces down here. Let's look at that a different way of kind of showing that. The T that's left is, we're going to create that by removing remove that chunk, and we're going to remove that chunk. So where are the centroids of those 2 pieces? So they're going to be over 1.5, right? Because we're at 3, so they're going to be along that axis. But they're going to be, this is 2, so our height here is 8. So let's come over 1.5. And then up 4. So the centroid of this red part that we're moving is right there. And equivalently, the centroid of this blue part that we're removing, so again 1.5, so there's the centroid of the blue part. Those two centroids are not on the axis or the neutral axis of the overall rectangle. And so that tells us that when we subtract these two, the centroid is going to move. This T shape, its centroid is not going to be located here. And you can kind of see that if you look at it intuitively, thinking about, remember what a centroid means, is it's a point about which everything balances. When we cut these two away, if we tried to balance it over here, the whole shape's going to tip that way, right? Because we don't have an equivalent area for this down here to balance it. So our centroid is going to have to shift up. So the first step, anytime we're looking at a composite shape that has a centroid different than the original shape, we have to find where the neutral axis of the final shape is. So remember, the formula for finding the centroid of an object is y bar is equal to the sum of the individual y's for each component piece times the area of each component piece divided by the sum of the area. So another way you might see that is it's a weighted area, or first moment of inertia, but that kind of confuses it with I, so we usually just call it the centroid. So let's look at that. Let's break this into pieces. We want to find y bar for this composite piece. For me, I always make my reference point for when I'm finding y bar from the bottom of the shape. You could do it from the top here. It shouldn't make any difference how you do it. You can go back and look at the centroid video if you don't believe me about that or don't remember how to verify that you can do centroid from either direction. So I'm going to use my reference point as here at the bottom to find centroid. So first area is going to be equal to, let's look at the area of this top flange. So its centroid, we know, is going to be located at the location somewhere right about there, right? It'll be centered because it's symmetrical and up 1 from there. So the distance from the bottom of the shape to the centroid of this upper, let's add some color here. So distance from here up to this centroid. So this is the centroidal neutral axis of just that top flange. That distance is going to be equal to, from here to here is 8 plus another 1. So the area for that area, or the distance for that area, is going to be 9 centimeters. Times the area of that is 2 times 8, so 16 centimeters squared. And then plus, now we need to look at, let's look at this orange piece. So here we're going to be distance to the centroid of the orange piece. This is 8, so it's going to be up 4. So there's the centroid of this one. So here we're looking at from the bottom up, that's 4 centimeters, times the area of this one is, again, 2 times 8, so times 16 centimeters squared. And all of that's over the sum of the areas. So that's over 16 plus 16. Okay, so let's figure out what that comes out to. 9 times 16 plus 4 times 16 divided by 32. So y bar is equal to 6.5 inches. So originally our neutral axis of a big rectangle 8 by 10 would have been 5 inches. Now we have found our composite y bar for this final T shape is at 6.5 inches up from my reference. I did 9 and 4, both off of the bottom, so that's where I'm measuring for my 6.5 from. So I come up 6.5 from the bottom, and right there is my new centroid of the composite shape. So this is the neutral axis for my composite shape. Okay, and why I have to find that is now when I'm looking for I for this composite shape, I'm always looking for I about the neutral axis of the shape that's being bent. So in this case, I had to find where that neutral axis was located. And again, I did it by adding up these two component areas. I could have found the centroid by finding centroid at the big and then subtracting these two. Again, you can do it either way. You can do it reference from top or bottom. However you do it, though, you should find out that the centroid is 6.5 inches up from the bottom, located on the axis of symmetry. Okay, now that we have y bar, we can start looking at I. So if you think back to the I of the total rectangle, that was 666.66. You might think that what we're going to do is take that I and subtract out the I's of these individual pieces. But we actually can't do that because that 666 was I about this neutral axis. So if we wanted to do that, we would have to find out what the effect of this area was about our new neutral axis. And we'll look at that maybe in a minute, do it that way. But for now, we're going to do it by building up I from the components, this purple rectangle and this orange rectangle, just like we did to find the y bar or composite centroid. So let's look at the impact of each of these shapes on I. We'll start by looking at the top flange. So I for the purple top flange is going to be equal to, first we figure out the moment of inertia about its own centroidal axis. So we know that's 1/12 times the base, the length parallel to the axis. So that's 8 times the height cubed. So that's times 2 cubed. And then that part right there gives us the I about this axis. But I want to know what I is about the neutral axis of the whole shape. So that means I have to use the parallel axis theorem. So I add on the plus AD squared part, A times D squared. So the area of the part that I'm looking at is 16 centimeters squared. So 16 times the distance. Now the distance that this refers to is the distance from the centroid of the piece I'm looking at to the centroid on the axis that I care about, the neutral axis. So in this case, the distance would be 9 minus 6.5, right? That's the distance. 9 inches or 9 centimeters gets us up to the neutral axis of the top flange, and 6.5 gets us up to the neutral axis of the composite shape. So 9 minus 6.5 will give me this 2.5 inches here from centroid of the component piece to centroid of the composite piece. So all of that is the contribution of this top flange to moment of inertia about the neutral axis. So let's plug in values for that. That would be 8 times 2 cubed divided by 12 plus 16 times 2, oh, I've left off my squared, times 2.5 squared. That's equal to 105.33 centimeters to the fourth. That is now the I contribution for the purple flange about the neutral axis. So we said this first part gets us I about its own centroid, and then the second part here shifts that axis to be about the neutral axis of the shape. Okay, now we can do the same thing for the orange. I orange is equal to 1/12 its base, 2, times its height, 8 again, cubed. That gets us the I about that axis, its own centroid. That's about that axis. But we want it about this axis up here, so that's going to be plus its area, which again is 8 times 2, so 16 times the distance from this centroid to this centroid. So in this case, this is 6.5 inches, or centimeters, sorry, minus centroid of this one would be 4, all that squared. So let's figure out what that is. 8 cubed times 2 divided by 12 plus 16 times 2.5 squared. So that's 185.33 centimeters to the fourth. So we already figured out that's the I about its own centroid. Then this part takes that and shifts that I to be about the neutral axis. So now the total I about the neutral axis is equal to 105.33 plus 185.33 equals 290.66 centimeters to the fourth. That is I about the neutral axis. So that is the I we would use to find bending stresses, shear stresses, etc. Let's look at it. We could have done that a second way, right? So rather than look at the component I's and add these two together, I could have also done it by looking at the overall I and then subtracting these two sides. I just want to make the distinction. This is different than when we were looking at this overall one. Here, I could find the overall I for the whole rectangle and subtract these two directly from that I because they all shared their centroids along the same neutral axis or centroid of the original parent shape. That's not the case now. Let's look at what I mean a little more closely. So we still have an axis of symmetry right here through the middle, right? If we look at it's over 4 in the x direction and then 5. So there's our axis of symmetry, and here at 5, that is the centroid of the whole 8 by 10, but we found that the centroid of our composite shape is actually up at 6.5. So that's that final centroid of the shape that we really want, the one that we're looking for at the end, is up here at 6.5. And then let's try to use consistent colors here. The centroids of each of these areas are over 1.5 and up 4. So right there and roughly right there. So you can see none of these share the same neutral axis. So for each piece of this, when I'm looking at it for adding or subtracting pieces, I need to use the parallel axis theorem. Let's go ahead and do it that way. I just want to point that out now that we have a bunch of different centroid distances and neutral axes. So this is a centroid distance for these two pieces we're cutting out. This is the centroid distance of the original overall 8 by 10 rectangle. And then this is the actual centroid and neutral axis of the final composite shape. So this is the one that we want to find I about. Okay, so let's look at that. We want this way, this time, instead of doing like we did above and adding together two component I's, what we're looking at now is I want to show you how to do it. We could find the I of the big rectangle and subtract out these two pieces. So let's find I of the big rectangle, but about the neutral axis of the composite shape. So I, big rectangle, big blue shape basically, is equal to 1/12, the base, 8, times the height, 10, cubed. That is the moment of inertia of this shape about its own centroidal axis right here. That's not the one we want to know about. We want to know about the neutral axis of the final shape. So I do need to use the parallel axis theorem here. So it's going to be plus its area, 80, times the distance from the centroidal axis of the shape we're looking at to the neutral axis of the composite shape. So that's this distance between here and here. So this one's at 5, this one's at 6.5. So that's 6.5 minus 5. And that distance squared. Okay, so let's plug values in for that. 10 cubed times 8 divided by 12 plus 80 times 1.5 squared. And that comes out to 846.66 repeating centimeters to the fourth. Okay, I want to point out here, that's a different number than I about its own neutral axis. Remember when we were back looking at I for this whole rectangle, that's 666.66 centimeters to the fourth. This is the same shape, but we're looking at it about a different neutral axis. So it's a different value. Okay, now let's look at I for this red shape. So I for the red part is equal to 1/12. Its base is 3 times its height is 8 cubed. Okay, so that is its I about this axis right here. So that's not the axis I care about. I care about the neutral axis up here. So again, I'm using parallel axis theorem. So plus its area is 3 times 8, so that's 24, times the distance from this centroid to this centroid, and that is, this one's at 4, and this one's at 6.5, so 6.5 minus 4 squared equals, okay, 8 cubed times 3 divided by 12 plus 24 times 2.5 squared, and that is 278. Okay, I could repeat all the math for the blue one, this rectangle right here, but you can see it's identical to the red one, it's just on the opposite side. So I'm just going to multiply this one times 2. So our I total is going to be equal to 846.66 minus 2 times, because this one and this 2, so 2 times 278 equals, so 846.66 minus 2 times the answer, and I get that I total is equal to 290.66 centimeters to the fourth. Okay, so again, you can see same answer, just came to it a different way. Key idea here, now that our component pieces have a centroid located at a different distance from X than the centroid of the composite piece, the final shape, we have to use the parallel axis theorem for every term of I. You can see that every I that we used, we get I about its centroid axis, and then we shift that I to a new axis. So this part right here shifts this I from about this axis down to this axis. This part here shifts this from this axis up to this one. Same thing here. This part shifts this I from the total, the original neutral axis, up to the neutral axis of the component. This one shifts this I up to here, and we end up with the same answer. Okay, hope that makes sense for a T shape. The last shape we're going to look at is one that's quite a bit more complicated, just to show you it really doesn't matter how weird the shape gets. You can still turn it into I about the neutral axis by using component pieces. Okay, so for our last shape, let's look at this very odd shaped cross section that I've come up with here. You can see how I've tried to represent it. There's basically a hollow pipe on the top, outer diameter 5 centimeters. There's an inner diameter of 2 centimeters that's hollow. Then you've got a 1 centimeter wide web basically, and then kind of a weird trapezoidal triangular shape for a bottom flange down here. So first step, as with any shape that we're trying to find, is we need to find the centroid of the composite shape, because that's where the neutral axis will be. And when we're looking to find I, or moment of inertia, it's always about the neutral axis. So first step of any composite shape when you're looking for I is first you have to find y bar to find the neutral axis of the composite shape. Remember that y bar is equal to the individual y's, sum of the individual y's times the individual areas, divided by the sum of the areas. And so if we have a complicated shape like this, we'll typically set up a table format to find y bar. So I'll say first column will be the name of the area. Second will be the distance from the bottom. I always use the lower edge of the section as my reference point. So that's going to be a distance, the individual y bars, you can say it. And then we'll have the area of each area. And then we multiply those together to get the last column is the individual y times area. Okay. So set this up in a table. Okay, so let's break it into areas now. So to start with, let's look at this outer diameter, kind of shade this in. That's going to be one area. We'll call that just the blue area. Then we're going to subtract from that the hollow area inside it. So that'll be another area, the red area. And then let's look at this web. And to make it easy, you could see I could find I of the trapezoid, but in my mind, it's easier to just kind of imagine this web continuing on running down through. And that breaks this shape into a rectangular section, though. So that's one area. That's the orange area. And then we'll look at these triangles as another area. And I'm going to shade them both as purple because they are symmetric about this axis. So if I find the value, the component for one of them, I can just multiply it times 2, and that'll be for the other as well. Okay, so let's start figuring out the individual centroids and areas of each of these. So for the blue shape, its centroid, circles are easy, right? Centroid's always right in the center of the circle. So its distance is from my reference. We're saying that's from the bottom here up to its centroid. So that's 3 plus 8 plus half of 5. So 3 plus 8 is 11 plus 2.5. So that distance is going to be 13.5 centimeters. its area is going to be pi r squared. So radius is 2 if diameter is 5. So r squared is 2.5 squared times pi. So the answer for area is 19.635. Multiply those two columns together to get the third column. So times 13.5. And that is equal to 265.072. Okay, now for the red. Its centroid, right? It's going to share its centroid with the blue area because they're concentric circles. So distance to its centroid is 13.5. Its area is, again, pi r squared, but now r, if it's a 2 centimeter diameter, r is going to be 1. So 1 squared is 1 times pi. So basically it's 3. So just it's the value, its area is just pi, which is 3.14159. So we'll say that's 3.1416 basically times 13.5. So that value is, oh, and this is a negative. That's important to point out here because I'm subtracting this area, right? It's a hollow part of the beam, so it doesn't contribute to bending stiffness. It's counteracting, it's basically taking away that same amount of area that we included in the blue circle. So it's a negative area. So when I multiply through, that's a negative 42.412. Okay, let's look at orange now. Centroid of orange is going to be, this is 3 plus 8, so that's 11. So centroid of it would be up 5.5. So that is right there. So distance, we said 5.5. Its area is 11 times 1 centimeter. So that's 11. Sorry. So 11 times 5.5. That's equal to 60.5. Okay, and now we're down to the purple. And you can hopefully remember that the centroid of a triangle is located 1/3 up from its base. So here it's 3 centimeters height. So its centroid axis is 1 centimeter up. So its centroid is 1/3 in each direction. And this is 6 minus 1, so 2.5, 1/3 of 2.5. That is 0.833, so it's right about in there, but really I only care about y because I have symmetry about these two. So my distance here is just 1. So purple area, distance is 1. The area of it is going to be equal to, so area is 3 times 2.5. And then, so that's 7.5 would be the square area of that, or rectangle. But it's a triangle, I divide it by 2, but there's 2 of them, so I'm just going to leave it as that. So say the area of both of these, since that's basically what it is, it's those 2, area is 7.5, and multiply that through, that's going to be 7.5. Okay, so now I can sum all of those up. I'll sum the right 2 columns, really, or what I need, right? Because this is what I'm looking for, the sum of y times a, so that's the sum of this column, divided by the sum of the areas, so that's this column. So let's add that up, 19.635 plus 3.1416 plus 11 plus 7.5. So we get, I think I typo there. Let's do that again. 19.635 plus, oh, that's minus. That's what I did wrong. Minus 3.1416 plus 11 plus 7.5. That looks better. 34.993. That's centimeters squared. So just, again, a note, I typed it in wrong. I missed the negative sign the first time because it's a negative area subtracting from that overall circle. Okay, do the same thing here. 265.072 minus 42.412 plus 60.5 plus 7.5 equals 290.66 centimeters. This will be cubed. Okay, so then y bar is equal to, let's just move these up here, 290.66, that's centimeters cubed, divided by 34.993, that's centimeters squared. So our units are going to come out to centimeters, which is good, right? We're looking for a length distance, divided by 34.993. So I get my y bar is equal to 8.306 centimeters. So we can measure up for that now and mark our composite centroid at 8.31 centimeters. So 8.3. So right there is my centroid. So this is my neutral axis of this composite shape. Reminder, I had to find that first before I can solve for I, because I is always about the neutral axis. So now let's start looking at the contributions of the individual shapes to I. Okay, again, we'll look at I for the blue area first. And we haven't looked at a circle yet in this video, so we'll come back to my textbook, find the equation for I for a circle is I is 1/4 pi r to the 4th power. So let's plug in our numbers for what that would be here. So I for the blue circle is equal to 1/4 times pi times the radius to the 4th. So the radius of the blue area is 2.5 to the 4th. Okay, that gets us I about its own centroid. So that gets us I about there. But we want to know I about the neutral axis of the composite shape. So we're going to have to use parallel axis theorem. So that's plus the area. Area of a circle is pi r squared. So that will be pi times the radius of 2.5 squared. That gets us our area. Now we need to know the distance from the centroid of the area we're looking at to the centroid of the composite shape. So that's going to be equal to, this distance here is 3 plus 8 plus half of 5, so we already found that, that's 13.5, minus the distance to the neutral axis. We just found that at 8.306, minus 8.306. And that distance is squared. Remember, I, let's write that up just here. I about neutral axis equals I about its own axis plus area times distance squared. Okay, so we can, that's I for the blue circle. Now let's do for the red. Again, it's a circle, so I is equal to 1/4 pi times the radius to the 4th. The radius of the red circle is 1, so that's kind of easy. 1 to the 4th will be 1. But again, that is about its neutral axis, centroidal axis right there. So I need to shift that down to here. So once again, it's area, which is pi times radius, in this case, is 1 squared. That just gets us the A part of the parallel axis theorem. And then times d squared. And the d is going to be the same as it was for blue, right? Because they share a centroid. So 13.5 minus 8.306, that distance squared. That's the I for the red part. And that whole I we can say is going to be negative when we add it together, right? Because we're getting that, we're subtracting that from the total I of the shape. Okay, let's move on to orange. I orange, okay, this is a rectangle area, we know that one, equals 1/12 its base, so that's 1 centimeter, times its height, that's 11 centimeters cubed. That gets us I about its own centroid. That's I about that axis, but we want it about this axis, so we have to do parallel axis. So plus its area, 1 times 11, so 11 times the distance. So in this case, the distance is 8.306 minus the distance from here to here, which is 5.5, and then that's squared. That's the orange component. Okay, we're on to our last component now. I, for the triangles, is going to be equal to, I'm going to start out just by saying 2, multiplying 2 times I, because I'm going to find I of one triangle. We haven't done a triangle yet, so we need to find that. Looking at triangle, I is 136 BH cubed. Okay, so 136 times the base, this was 2.5, times the height cubed. So the height of this triangle is 3 centimeters, so 3 cubed. That gets me I about that axis right there. But again, I care about it about the neutral axis, so I have to do parallel axis theorem. So it's going to be equal to the area of one triangle, because I did the multiplying by 2 outside this, so I'm just looking at one triangle right now, which area of one triangle is 2.5 times 3 divided by 2, so its area is 3.75 centimeters squared, times the distance from this centroid to the neutral axis of the composite shape. So that distance is 8.306 minus this distance here was 1 centimeter, 1/3 of its height. It's 3 centimeters, so minus 1. And then that distance squared, right? It's always d squared equals. Okay, so let's plug in values and figure out how each of these contributes I to the total shape. So we'll start by finding this part here, I of the circle about its own neutral axis. That's 2.5 to the 4th times pi, all that divided by 4, and then plus pi times 2.5 squared times 13.5 minus 8.306. Get all of that is equal to, oh, sorry, I plugged in a number wrong there. Let's try that again. I'll do it. It's easier to go the other direction, I think. 13.5 minus 8.306, that squared, times 2.5 squared, times pi, plus 0.25 times pi times 2.5 to the 4th. That looks like a better scale number, 560.38. And that's centimeters to the 4th. Okay, then we'll do it for red. I'm just going to write the negative right now so I don't forget it. Negative 13.5 minus 8.306, that squared, times 1 squared, times pi, plus 1 to the 4th, times pi, times 0.25. And that comes out to 85.538. Again, centimeters to the 4th. Okay, on to the orange part. 8.306 minus 5.5 squared times 11 plus 11 cubed times 1, times 1 times 1 divided by 12. And that equals 197.527 centimeters to the fourth. On to our last part. Purple, 8.306 minus 1, that squared, times 3.75, plus 3 cubed, times 2.5 times 1 divided by 36. All of that times 2. This equals 404.082 centimeters to the fourth. Okay, these are the individual contributions of each shape. So let's just look at the terms. This term right here finds me I of the blue area about its own neutral axis. This part here takes and shifts that I from about its neutral axis to about the neutral axis of the composite shape. Same thing with the red. This part right here gives me the moment of inertia of the red area about its own neutral axis. This second term, the parallel axis theorem part, shifts that I from about this axis down to about the neutral axis of the composite shape. This term right here gives me the moment of inertia of the orange rectangle about its own centroid, and then the second half of the orange equation shifts this I from being about this axis to being about this axis. Lastly, this here is I of one triangle about its own central axis. This chunk here shifts it, the moment of inertia, from about this axis to about this axis. So add those two together, you get the contribution of one triangle about this neutral axis. And then you multiply it times 2 because I have 2 of those triangles here. I could multiply it times 3 if I had some weird shape that had another triangle right out here, or times 4 if I had another triangle over here. The key idea is I can't, let's say I had another triangle right here, even though that area of the triangle is the same, I can't just add that on as a 3 here because its centroid is a different distance away from the neutral axis than this one is. So when things share a centroidal axis, you can just multiply them together. You can't if they have a different distance from the neutral axis. Okay, so let's add together all these pieces. I total is equal to 560.38 plus, actually minus, so we're at the red section now, minus 85.538 plus 197.527 plus 404.082. So I total about the neutral axis is equal to 560.38 minus 85.538 plus 197.527 plus 404.082 equals 1076.5 centimeters to the fourth. That is this bending stiffness basically of this shape about its neutral axis. So you can see you can take pretty much any weird but geometric shape and find, first you find its centroid using first moment area basically, and then you find its moment of inertia, what we call the moment of inertia, which is really the second moment of area. Another way of saying I, we haven't really talked about this, we say y bar up here, y bar equals the sum of the individual y times the area over the sum of the areas. That's, like I said once before, that's really the first basically moment area about the neutral axis, right? We're taking an area, multiplying it by a distance. So if you think back to moment is a distance times a force, this is kind of like the moment of an area divided by the area. I is what we call the second moment area. So it's really the sum of y squared times the area over the sum of the areas. So kind of a very similar concept, except this one has a physical representation, right? That's the balance point of the shape. This one is a geometric property, but not a physical property that you can visualize or measure. Okay, so that's our total. So we've shown how to do a complicated shape like this. I want to point out that in reality, you're not going to hand find the centroid and the moment of inertia of a weird shape like this. It's much faster, more accurate, and more efficient to do this in a solid modeling program. So, for example, I'll open up SolidWorks here. Let's take a look at SolidWorks. So here in SolidWorks, you can see I have modeled the same shape that we just did by hand, and modeling the shape, takes maybe 90 seconds or something. And then if I just select the face of it, come up here to evaluate and look at section properties, it does all of the math instantaneously for me, and it found my distance of my centroid is 8.306. And if we think back to what we calculated over here, we calculated 8.306, it came up to 8.31. It looks like it's rounding a little more. Let's see if I can change my custom. Yeah, let's increase our decimal places. Okay, so there you can see it came up with 8.3067, so it's a little more accurate than I was in my rounding there, is the distance to the centroid. And then its moment of inertia is 1076.5062, and we came up with 1076.5. And you can see we did it just about an axis parallel to x, but it's at the same time calculating as if we were bending about y or if we were bending about z. Z doesn't make much sense for us because we're looking at a two-dimensional shape there. But here is a great example of how much different the bending stiffness is on this shape. About an axis parallel to x at the neutral axis, it's 1076, versus about an axis parallel to y, it's only 46. Again, just another example. What matters for the stiffness of a shape is how much of its area is located far away from the neutral axis of the shape. Okay, I think that's probably enough about finding moment of inertia of a shape. Remember, general idea, moment of inertia is a representative property of the stiffness of a section about bending. So we can find it by looking at the composite pieces. First step is always to find the centroid of the composite shape. Then once you've found the centroid of the composite shape, you figure out the contribution each shape has to the moment of inertia about that centroid of the composite, of the neutral axis of the whole piece. So, and you do that using the parallel axis theorem. So, pretty long video looking at moment of inertia, but I hope that helps clarify any confusion you have on how do you find moment of inertia of shapes.